All right, continuing on with our types of reactions, we have two left, and both of them are technically double replacement reactions. So double replacement is the second to last one, but more specifically, we're going to talk about the precipitation reaction. So a double replacement reaction is a chemical reaction where two elements in a different compound are going to switch spots. And so the key characteristic for this type of reaction is you're going to look for two compounds as reactants. And more specifically, the compounds themselves are going to be ionic. So remember, that's one metal and one nonmetal. If a precipitate is formed, and remember, a precipitate means solid, then it's going to be known specifically as a precipitation reaction. Now, how do you know if a solid is formed or not? We'll get to that. But let's first talk about the general form of a double replacement reaction. So you have your two compounds here, AB and CD. Remember, those represent ionic. And so in ionic compounds, remember the first element listed in the ionic compound, in this case A and C, they would be the metals. And so remember, just like single replacement, like replaces like. So the two metals are going to switch spots. And so you're going to see A is going to come over here and swap spots with element C, whatever that happens to be. And so you can see the reaction to that. CB is now the new compound, and then AD is the second new compound. Looking at a chemical example, we're taking a look at sodium sulfate reacting with aluminum chloride. So the sodium and the aluminum are the metals, and so those are going to be the ones to switch spots. Aluminum will come over here, take sodium's place, and sodium will come over here and take aluminum's place. Notice the subscripts here for sodium and for aluminum and even chlorine and even sulfate. The subscripts, other than the 4, because the 4 is part of sulfate, other than that, the subscripts can change depending on what they bond with on the product side. So what I mean by that is the sodium, there were 2 over here, but notice on the product side there's only 1. And that's because when sodium comes over here and bonds to chlorine, when sodium and chlorine make a compound, sodium's positive 1, chlorine's negative 1. So in the new compound, there's only 1 needed of each. For sulfate is negative 2 and aluminum is positive 3. So when aluminum comes here and bonds to sulfate, you can see that those subscripts need to change to accommodate the new species. And so just a quick reminder about that. Now, I talked about, you'll know it's a precipitation reaction if one of the products that's created is a precipitate or a solid. So how do you know if something is a precipitate or a solid? You need to use solubility rules. So those rules are listed here on the screen. They're also on the back of your periodic table. So these are given to you on an exam. And so let's go ahead and talk about these rules real quick, and then we'll look at some examples as to how you use them. So there are 7 rules, and if you look at the 7 rules, they're divided into 2 categories. So you'll see rules 1 through 4 on the left. This is going to fall in the generally soluble category. So what soluble means is that it's going to dissolve in water. In other words, it's going to be aqueous. It's not going to be a solid. But if it's insoluble, that's going to mean it doesn't dissolve in water, meaning it's going to remain as a solid. And that means it's a precipitate. So whatever compound you're looking at, you would just look to see, does it fall in the soluble category or the insoluble category? And that'll help you figure out if it's a precipitate being formed or not. Now, I want you to notice real quick on the rules, if you take a look at the solubility rules themselves, there's some patterns here. So if you take a look at the rules, almost all the rules that you see listed here have to deal with the anion, which is the negative ion. So starting with rule 2, every single one of these rules afterwards is looking at a compound that contains an anion. But rule number 1 is the only rule that deals with the positive ions. And that's actually pretty significant because that'll help save you a lot of time. Notice the ions that are listed in rule number 1, lithium, sodium, potassium. Those are alkali metals. And so a good rule of thumb is if a compound contains an alkali metal, such as the ones that are listed there, right away you know they're going to be aqueous. They're going to be soluble. So that'll help save you a lot of time when you're looking at products and having to figure out whether or not it's going to be aqueous or solid. And notice that's always. So there's no exceptions to that rule. You'll see that there are some rules, there are exceptions, but that one is always going to ring true. And so that, like I said, will help save you a lot of time. So how do we use these rules? Let's take a look at some examples. On this slide right here, we're going to look at example number 3, and I've got the solubility rules listed there as well, but you also have them on the back of your periodic table. What we're going to do is we're going to look at 9 compounds, and they're listed below right here. And what we're going to do is, using our solubility rules, we're going to figure out if these compounds would be aqueous or they would be solid if they were in a water solution. So looking at the first one, aluminum hydroxide, remember most of your solubility rules have to deal with the anion. So specifically in this example, I'm looking at what's the rule for hydroxide. And so the rule for hydroxide is over here. It's rule number 7, and it falls under the insoluble category. So any compound that contains hydroxide is generally going to be insoluble. Now there's some exceptions here, but notice aluminum is not one of the exceptions. And so because of that, this compound right here would be solid. Now, I'm not asking you to do this in this example. However, what if I were to ask you, what would that look like if you had to do a beaker drawing? Like if I asked you to show that in a particle form, what would that look like? Real simple, okay? You would just draw a beaker and then the aluminum hydroxide, and forgive my handwriting here, okay, you would just draw at the bottom and then you would draw a clump like over it. That indicates that it's not dissolving in water. It's staying intact. It's a precipitate. It's insoluble. It's going to be at the bottom. Let's take a look at this second one right here. Calcium nitrate. Once again, looking at nitrate, because like I said, all your rules are pretty much going to be for the anion, except for if it's rule number 1. Nitrate's right here. Okay, and nitrate falls in rule 2, which is soluble. Notice there are no exceptions here. So any compound that contains nitrate is going to be soluble, meaning aqueous. So if this substance was dropped in water, it's actually going to break apart. It's going to ionize. So if I asked you to draw calcium nitrate in a beaker drawing, what would that look like? Well, you would draw a beaker, and then instead of actually having the calcium nitrate clumped at the bottom, you would break it up into its ions. Make sure that you draw the ions, 1, with their charge, because they are ions now, but 2, make sure you draw the correct amount. If you look at calcium nitrate the way it's written here, there's 1 calcium, so I would draw Ca, and calcium has a positive 2 charge. And then there are 2 nitrates. And it's okay to just write the number 2 out in front and then just write nitrate -1. So that beaker drawing represents that it's aqueous, it's soluble, everything's going to ionize. We'll do one more and then I'm going to let you actually try some on your own. This one right here, potassium sulfide or K2S. Would that be soluble or insoluble? One thing I notice right away is that it contains an alkali metal, right? And so when I see that, automatically I know this is going to be aqueous. And so, like I said, I'm not going to draw the beaker drawings for every single one of these because that's not what the problem's asking. But if I were, I would draw 2 potassium ions and 1 sulfide ion broken up into beakers. So what I want you to do is pause the video right now and see if you can figure out the remaining 6, and then I'll reveal the answers afterwards. All right, we've got the answers for the remaining 6. The ones I have starred, I just want to cover real quickly because you may have gotten something different for those. So the phosphate one, this one, according to the rules right here, if you're looking at phosphate, it falls right here, okay, which is insoluble. But notice phosphate is bonded to lithium, and lithium is one of those ions that is always, this always is going to be the case. Lithium will always be, when it's in a compound, it will always be aqueous. And so that one might have been a little tricky. On the solubility notes that are given to you on the back of your periodic table, there actually is a little addendum to rule number 5. It'll say something like except, and then it will list some exceptions. So some students are worried like, wait, are any of these rules going to contradict each other? They won't. So don't worry about that. Silver sulfate right here, that one might be tricky because you look at sulfate right here, generally that would be soluble, but silver is one of the exceptions, so hopefully you caught that. Strontium hydroxide, same thing, hydroxides are generally insoluble, but strontium hydroxide is an exception, so that's why it's aqueous. And then finally, lead 2 iodide or PbI2. Any iodide containing compounds are generally soluble, but lead is an exception. It's listed right here. So that's the reason why it's solid. Now, what are we using all this for? Okay, what are these solubility rules getting at? Well, like I said, if a reaction creates a precipitate, it creates a solid, then it's known as a precipitation reaction. So when 2 aqueous ionic solutions are mixed together and an insoluble ionic compound forms, which we know as being a precipitate, then it's known as a precipitation reaction. And like I said, we use the solubility rules to predict the products. So let's take a look at this example right here. We have 2 aqueous solutions being reacted together. Okay, we have lead 2 nitrate and we have potassium iodide. We know they're aqueous here. we know that this is a double replacement reaction because it's two compounds, and the lead is going to take place of the potassium. Okay, so they're going to switch like that. So when lead comes over here and bonds to iodine, it creates PbI2. And if you look at your solubility rules for PbI2, which we just did, PbI2 is a solid. And so therefore, this would be a precipitation reaction. So what would this resulting beaker look like? Well, first of all, you would end up having the clump at the bottom here. And this is going to be where you would write PbI2. Notice I don't break anything apart, okay, because it's a solid. But then you also need to make sure this second product, and I put product in quotes for a reason there because you don't actually make anything. We'll talk about that in a moment. But this second part, that needs to be represented up here because aqueous means they're still in ion form. So the two will distribute. So there would be two potassium ions, okay, so 2K plus, and there's also two nitrates. Okay, that would be floating above still in solution, right? And so this is what your beaker drawings would look like. Notice you have, this is your first reactant, which is the PbNO3 2 up here. This is your second reactant, it's the 2Ki. And then when they come and bond, your solid, which is your actual product that you make, that's at the bottom, that's your precipitate. And then these ions up here, these two potassiums, and then these two nitrates. Do you notice how you started out with two nitrates and ended with two nitrates? And you started out with two potassiums and you ended with two potassiums. So nothing actually happened with those ions. It didn't make anything. It didn't create anything. So we give that a special name, and those are called spectator ions. Okay? Spectator ions. And that's on another slide, but I wanted to point that out now. Ions that do not create anything are spectator ions. All right, so wrapping up precipitation reactions, or getting to the end of that, if two aqueous solutions mix together and neither of the products on the right side make a precipitate, then we would actually classify that as no reaction, because in that case, all of the ions are spectator. Nothing's making anything. So when you're looking at predicting products like you are down here, you want to think, okay, is one of my products going to be a solid? Because if not, we would just write no reaction. So let's take a look at this first one. So the sodium is going to potentially switch spots with the calcium, right? So we need to kind of think through and say, okay, if sodium were to somehow bond to hydroxide, we don't have to think about it just yet specifically what the formula will be. Just think, if sodium bonded to hydroxide, would that create a solid product? And the answer hopefully is no, because right away, remember that sodium? Anything bonded to sodium, it's an alkali metal, it's not going to be solid. So right away, that's one product that's not solid. But what if calcium bonds to nitrate, right? Because the calcium is going to come over here and it's going to bond to nitrate. So maybe that might create a solid. So you look at your solubility rules and you would say, okay, does calcium, when it's bonded to nitrate, would that be a solid? And the answer is no. Look at where nitrate is. Nitrate is rule number 2. Anything bonded to nitrate is not going to be solid. And so in this first example, neither products are solid. They're both aqueous. And so for that, we're actually just going to write no reaction. If we look at the second one, though, which we're not going to do because it was on the previous screen here, okay, you can recall it's the same one. We've already worked that one out, obviously. It does create a solid. We've seen that on the previous slide, and so you would predict the products just like you normally would. All right, we are almost out of time for this reaction. The precipitation reactions have a lot to it, so I'm going to spend the last minute trying to cover this last slide here, and then we'll finish up maybe on the next video. So molecular equations, ionic equations, and net ionic equations. Molecular equations is simply a chemical equation. So when I tell you to write a chemical equation, that's what I'm asking you to do. It's a molecular equation. It's like potato, potato. So you can see that that's something that you're familiar with, right? But a total ionic equation, or sometimes we just say ionic equation, actually shows all these aqueous substances broken up into ions. And so you can see, rather than write PbNO3 like we do up here, we actually break it apart into ions. So you'll see there's the lead ion, and then there's the two nitrate ions. Notice we write the 2 out in front instead of as a subscript, because we're breaking it up into ions. Same thing, here's your reactant. You've got the 2 potassiums and the 2 iodines there. And then over here, this is still broken up into our 2 potassiums and 2 nitrates. and then you've got your precipitate, and notice it's held together. I'm going to finish up this reaction in the next video.